If you have not taken the exam yet, please remember that the testing center closes early on Mondays. They close at 7 o'clock on Mondays for FHE. The last test is given out at 6. I would suggest getting there before 6. The average lapse time so far has been an hour and a half, just what I anticipated it would be. But if you have not taken it yet, please don't procrastinate any more than you already have. Okay? So today we're going to start chapter 5, stereochemistry. This is a topic that we introduced on Friday, and we're going to elaborate on stereochemistry and its importance. We're going to talk about chirality, enantiomers, stereocenters, and a little bit of our favorite topic, nomenclature, learning some nomenclature dealing with stereocenters. Before we do any of that, we need 2 volunteers. I would like 2 right-handed volunteers. You don't have to be a baseball fan, but it helps. Okay, so we have 2 right here. Come on down. And please tell us your names as you're coming down. Okay, we got Tyler. And who's your favorite baseball team?
Mariners, Seattle Mariners.
Seattle Mariners. Okay, Tyler's a Mariners fan. Our other TA, Alex, is a big Washington sports fan. So, and? Morgan?
Yes.
And do you have a favorite baseball team?
No.
No favorite baseball team. That's okay. You can root for my favorite baseball team, the San Diego Padres. Usually, yes, I've seen your Padres hat before. It's a rare sight around here. Usually I don't pay any attention to baseball because the Padres are usually at the bottom, but this year they're looking good. Okay, so Morgan and Tyler, is that right? Why don't you just go to that aisle right there and play some catch, okay? Just play some catch with that softball. There's the room, there's nobody to hit, so, okay. Okay. That's why we do it off to the side. The softballs are a little clumsy sometimes. So while they're playing catch, we need another volunteer, a left-hander. Do we have any left-handers in the class? Okay, come on down. And okay, yeah, we need someone who throws left-handed. So what's your name? What's that? Tiankum. Okay, Tiankum is left-handed. Do you have a favorite baseball team?
Grew up in San Diego area.
Oh, good. Another Padres fan. Excellent. Okay. All right. So, Tiankum, we'll have you switch with Tyler. Okay? Yep. And Tyler, we have hand sanitizer out in the hall. So, in order to be COVID safe, we're asking everybody who participates to sanitize their hands and then come back. Okay? Yeah, we'll fill you in. All right. So, Tiankum is going to play catch with Morgan. Okay. Now, Tiankum, you told us that you're left-handed, but you're throwing with your right hand. Why? So that glove won't fit on your right hand?
Nope.
Why not?
The way that the glove is designed, the fingers, which any which side or left that way, set to go on the left.
Okay, so the glove only fits on your left hand, not on your right hand. Okay, so basically what you're telling us, go ahead and throw the ball a few more times. What you're telling us is that your hands are mirror images of each other that are non-superimposable, okay? And because your hands are non-superimposable mirror images, they only fit in one mirror image of a baseball mitt and not the other. Is that what you're saying? So you would need a mirror image baseball mitt to be able to put on your right hand, and that would let you throw with your left hand. Is that right? Okay, very good. Well, let's give all of our volunteers a hand, Tiankum and Morgan and Tyler. You two can go sanitize your hands and come back in. So we just learned the principle of chirality. So chiral comes from a Greek word meaning hand or handedness. An object is chiral if it is not superimposable on its mirror image. Okay, so we learned that our hands are chiral, mirror images, but they don't superimpose on each other. Okay, baseball mitts are also chiral. If we had a mirror image baseball mitt, it would not be superimposable, and it would fit on the right hand as opposed to the left hand. What other objects are chiral? Yes, please. Feet, exactly. Feet are also chiral. Have you ever tried to put a right shoe on a left foot? You have the same problem that you do if you try to put a baseball mitt on the opposite hand, because your feet and your shoes are chiral. Your shoes are mirror images. They don't superimpose. Okay? Anything else? Okay? What about golf clubs? If you golf, you've got to have the right set of golf clubs, whether you're right-handed or left-handed. Okay? Screws are also chiral, right? You can have a twist to the right or a twist to the left. Yes? What's that? Okay, your earlobes. It's pretty hard to superimpose your earlobes, but if you could detach them, you'd find they wouldn't superimpose. That's right, they're going to be chiral. What about cars? Have you ever driven a car in Japan or the United Kingdom before? There are mirror images of cars in the US. And I'll attest to you personally, they're very different. My brother lived in the UK years ago, and I visited him, and it was very disorienting to be on the wrong side of the car. I also lived in Japan and thankfully never drove a car while I was in Japan. I hope to never drive a car in that country. All right, so there are lots of objects that are chiral. And the reason we're talking about it today is because there are lots of organic molecules that are chiral as well. Chirality is a subtopic of stereochemistry, or the three-dimensional orientation of groups in space, okay? And differences in stereochemistry, small differences in stereochemistry can have a profound difference on the properties of molecules. We have an example here on the screen, two molecules, cellulose and amylose. These are both polymers, meaning they are very large molecules made up of a repeating unit. At the end of Chem 352M, we will learn that glucose is the repeating unit. We have a bunch of glucose molecules linked together, hundreds of them linked together, and that makes a cellulose molecule. Hundreds of glucose molecules linked together also makes an amylose molecule. The only difference is that the oxygen that's connecting these six-membered rings, right, these are chairs. These are not cyclohexanes because they have an oxygen in them. They're an ether, but they form a chair just like a cyclohexane would. You see that the oxygens in cellulose connecting the rings are equatorial with respect to both of the chairs that they're connected to. Here in amylose, you see that oxygen is equatorial with respect to one of the chairs and axial with respect to the other chair. So that equatorial axial connection gives amylose a different three-dimensional orientation than cellulose. So cellulose is going to be elongated. You're going to have a long strand. If you have hundreds of glucose molecules hooked together, you get a long strand. That strand has a slight twist. This tube model here shows us that. There's a slight twist, but it's elongated. What kind of intermolecular forces could two molecules of cellulose have with each other? If you remember the structure from the previous slide. Let's go back. What could we have? Hydrogen bonding, definitely. Okay, so what happens is that cellulose strands will hydrogen bond to each other. They'll get in close proximity because of that elongated structure. They can stack right next to each other, and you get fibers. So you get very strong fibers that are held together by lots and lots of hydrogen bonds. What is cellulose a component of? Okay, so yeah, cells. Can we be more specific? Cell walls, okay. So cell walls, those are pretty tough materials, right? So it's in plants. It's also the main component of cotton. About 90% of cotton is cellulose. And wood, about 30 to 40% of wood is going to be cellulose, okay? And so cellulose is a structural polymer in that it provides a certain structure to the materials that it's made up of, or that it makes up. Okay, so is cellulose going to be water soluble? It should be, but have you tried to dissolve cotton in water? That would really stink if you try to wash your cotton t-shirt and it dissolved. Okay, has that ever happened to you? No. Okay, so has you ever seen wood dissolve in water? That would also stink, right? Columbus never would have made it to America if wood dissolved in water. So obviously it doesn't. We know that cellulose does not dissolve in water. But if we look at its structure, we would think that it would. Why does it not dissolve in water? Any ideas? Okay.
I'm not sure, but does it hydrogen bond with itself? So it doesn't have room for the water molecules to come in?
Yes, you're exactly correct. So the OH groups in cellulose most of them are tied up in hydrogen bonds to other strands of cellulose to make those fibers. So there's very few OH groups in cellulose that would be available to hydrogen bond to water. So that is why cellulose is not going to dissolve in water. It can absorb water because there's a little bit of some of those OH groups available, right? Cotton t-shirts will absorb sweat. If you work out in a cotton t-shirt and you sweat, it'll be absorbed by your shirt. And that's because that's just not nearly as many water molecules as if you were to dunk your shirt in a big bucket or in a washing machine or something like that. Okay, so it can absorb moisture because it has a few OH groups available, but it will not dissolve in water. Okay, so the properties of cellulose are dictated largely by its three-dimensional orientation in space or its stereochemistry. And it's a tough material. It's not very elastic. You can't stretch out wood very well. Cotton is also not that easy to stretch out. And that's because it's already elongated in its form. Okay. All right, amylose or starch. Let's talk about that. Starch is present in potatoes and in other vegetables. Does starch dissolve in water? Have you ever cooked with starch before? Have you added starch to water? It will dissolve. It thickens it up, but it will dissolve to a certain extent. So we see a difference in properties right away. And we see the way we've drawn this here, instead of being elongated, our starch molecule is going to be more helical in nature. Okay? We can see that here on this tube-like model. We get a helix that forms by having that oxygen axial with respect to one ring and equatorial with respect to the other. So there'll be you'll have some hydrogen bonds across the turns of the helix to stabilize that helical shape, but most of the OH groups are going to be available to hydrogen bond to water. So there's difference number one with amylose versus cellulose. Okay? Difference number two is it is stretchy, it can be elongated, and it can also be packed more tightly. Okay? And that influences what amylose is used for. It's used as a place to store glucose molecules that are later broken down and used for energy. Our body can chop up amylose. It can remove, whoops, I went the wrong way. It can remove the individual glucose units from amylose and then metabolize them to get energy. And you can pack those glucose units tightly in the body by having this helical structure that can be squished down and compressed better than you could with those tough fibers of cellulose. Okay? So different structures, different stereochemistry, three-dimensional orientation, vastly different properties by making a polymer of the same material. So that tells us how important stereochemistry is. Okay? Speaking of enzymes breaking these molecules down, we know that we have enzymes that can help us digest starch and liberate those glucose molecules from starch. What about cellulose? Can we eat cotton? Can we eat wood? We certainly cannot. Termites can. So termites have the enzymes that can chop cellulose up, but humans and mammals do not have that. Okay? So stereochemistry makes a big difference. Small differences in stereochemistry make a big difference in the properties of molecules. So let's review briefly what we've learned about stereochemistry so far. On Friday, we introduced the term stereoisomers. Remember, constitutional isomers, same molecular formula, different connectivity of the atoms. Stereoisomers, same molecular formula, atoms are connected together in the same way, but they're oriented differently in space. The book points out another way to tell the difference here. Constitutional isomers are going to have different IUPAC names, whereas stereoisomers will have the same name except for prefixes such as cis or trans, and prefixes such as R or S, which we don't know yet, but we'll learn those by the end of class today. Okay? So the prefix, the very, very beginning of the prefix before the numbers, is the only thing that is different if we have compounds that are stereoisomers of each other. Okay? So we need to learn some vocabulary for talking about stereoisomers. The first vocabulary word we'll learn, well, we've already learned chiral. I guess that's the first one. Our second one for the day is enantiomers. Okay? Enantiomers are stereoisomers that are related as a molecule and its non-superimposable mirror image. Okay? So if our hands were molecules, they would be enantiomers. They're non-superimposable mirror images. Okay? So I have some models here today, and we're going to demonstrate this principle of enantiomers and non-superimposable mirror images. So first, let's look at bromochloromethane, CH2BrCl. Okay, I've made the mirror images of bromochloropropane. So the black bonds are representing bonds to hydrogens. Red's going to be bromine, and yellow is going to be chlorine. Okay? So I have these mirror images. And now we need to see if they superimpose on each other. Do they superimpose? Okay? So are these enantiomers? No, these are not enantiomers. And that also tells us that bromochloromethane is achiral. It is not a chiral molecule because it's superimposable on its mirror image. Okay? Let's replace one of our hydrogens with a fluorine. The fluorine is going to be purple. Connect that on. Okay. So now we have bromochlorofluoromethane. Okay. Mirror images. Let's see if they're superimposable. Can we superimpose these mirror images? We cannot. Okay. So bromochlorofluoromethane is chiral. And these are the two enantiomers, the two non-superimposable mirror images of bromochlorofluoromethane. Okay? Question, Morgan. They are closely related. A chiral molecule will have two enantiomers, okay? Two different mirror image forms that are non-superimposable. So if a molecule is chiral, it has its enantiomers, and these are different compounds. We'll talk on Wednesday about the properties of enantiomers. Many of their properties are the same, but some are different. They are not the same compound, okay? So a chiral molecule will always have two enantiomers. An achiral molecule, the term enantiomers does not apply because the mirror images are superimposable. Okay? Other questions? All right. So, yes, please.
So how would we name two different stereoisomers?
That's a great question. By the end of class today, we'll have that answered for you. But we haven't learned the nomenclature yet that we need to name them. So something you might have noticed when I replaced a hydrogen with a fluorine, I created a carbon that has 4 different groups attached to it. In bromochlorofluoromethane, we have 4 different groups attached to this carbon. That is known as a stereocenter. Stereocenter, our third vocabulary word, atom with 4 different groups. It doesn't have to be 4 different atoms, 4 different groups, as we'll see in a minute, attached to it. Okay. Your book refers to these as stereogenic centers. There's lots of different ways. Some books call them chiral centers or chirality centers. Stereocenter is the term that I prefer. Stereogenic center is just as good, but it's longer, so I typically like to say stereocenter, but either of those terms will work for purposes of the class, okay? So any atom with 4 different groups attached to it is going to be a stereocenter. And the presence of stereocenters is connected to whether or not a molecule is chiral, okay? So if there are no stereocenters in a molecule, that molecule is usually achiral. What I mean by usually is for purposes of the class, we will not encounter chiral molecules with no stereocenters. But there's some exotic forms of chirality that do exist. So there are molecules in the world that have no stereocenters that are actually chiral. We just won't encounter them in this class. If you go on and study organic chemistry at a more advanced level, then you would learn about some of those other types of molecules with this exotic chirality. But for now, in this class, no stereocenters, the molecule would be achiral. So that's what I mean by this statement. If there's one stereocenter, then those molecules will always be chiral. Okay? And this may seem unusual. It'll make more sense on Wednesday when we talk about these compounds. If we have 2 or more stereocenters, the compound may or may not be chiral. Okay? The reason for that is sometimes when we have 2 or more stereocenters, we introduce an element of symmetry. And what we find is that if we have a plane of symmetry in a molecule, then that compound is achiral. A plane of symmetry makes it achiral. So let's draw bromochloromethane on the board and see if we can spot the plane of symmetry that makes it achiral. And I already messed up. I can't have 2 wedges coming off of that thing, or 2 dashes. I have to have a wedge and a dash, okay? So where's the plane of symmetry in bromochloromethane? Okay, so right down the middle, is it parallel to the board or perpendicular to the board? Parallel, it's in the plane of the board, right? So the plane of symmetry is in the plane of the board because what's reflected, what the part of the molecule that's not in that plane, that's reflected on itself is the same, right? So the plane of symmetry in this molecule is in the plane of the board. Let's draw bromochlorofluoromethane. What happened to our plane of symmetry? It is gone. We now have fluorine reflecting on hydrogen. Those are not the same, so there's no plane of symmetry in this molecule. Okay? So if we have a plane of symmetry, the molecule will be achiral. If we don't have a plane of symmetry, it will be chiral. When we have one stereocenter, we are not going to have a plane of symmetry. Okay. So there's a bullet point table here summarizing what we have discussed so far relating to stereochemistry. So you should read through these points and hopefully they will make sense. If not, then please ask questions. Please review until these points are clear to you. Okay? All right, so how can we recognize and draw stereocenters? It's important to be able to recognize stereocenters as well as draw them. So, question.
When you wrote the definition for stereocenter, it says with four different groups. In that case, would this bromochloro one without one chlorine not be a stereocenter?
This one right here?
Yeah.
Correct. That is not a stereocenter.
Okay.
And so that's no stereocenter, plane of symmetry, achiral. All those things are connected. And then over here, we have no plane of symmetry, stereocenter, and chiral. Those three things are also connected. So to draw first of all, recognizing stereocenters, it's got to be four different groups, okay? Not necessarily four different atoms. Okay, this compound here, we haven't learned how to name alcohols yet, but it's called 2-butanol. That's something that'll come later. I've circled carbon number 2 in this compound. Is carbon number 2 a stereocenter? Yes. Why? What are the four different groups? Who can raise their hand and tell us? Yes, please. Okay, so we have the OH group. We have the hydrogen that's implied that we didn't draw. And then these are both carbons, but this is an ethyl group and that's a methyl group. So this is indeed a stereocenter. Four different groups are attached. And that means that 2-butanol is chiral. The two mirror images will be non-superimposable. Okay? What if we extend the chain by one carbon? Stereocenter, yes or no? No. Now we have two ethyl groups. This molecule would be called 3-pentanol. That is achiral. And you'll notice the way I've drawn it, you can see the plane of symmetry cutting through the middle. Okay? So, four different groups, not necessarily four different atoms. So how do we draw enantiomers? Well, the simplest way to do it is to just draw one form using wedges and dashes. So let's take our 2-butanol over here. And I've used wedges and dashes to draw that. Then we can make an imaginary mirror. And then on the other side of our imaginary mirror, we draw the mirror image. You don't have to make the imaginary mirror if you don't want to, but you want to make the chain in a mirror image of what you've drawn on the left. And then you want to make the substituents appear in a mirror image of what you've drawn on the left. Okay? And what you'll find is that these are non-superimposable mirror images. And you can do this with models as well. It doesn't have to just be on paper. That was how I created the mirror images, the enantiomers of our bromochlorofluoropropane. I made sure that when I constructed them, that I had constructed mirror images. And since I knew that the carbons were stereocenters, by constructing the mirror images, I ended up with enantiomers that are not superimposable. Okay? So, draw one, make an imaginary mirror if you want to, draw the other. Okay? Now, we can have stereocenters in rings as well as in chains. Identifying a stereocenter in a ring is a little bit different than identifying a stereocenter in a chain. What we need for an atom in a ring to be a stereocenter is we have to have two different groups coming off of that carbon, two different substituents, okay? So let's draw the cyclic compound. This is methyl cyclohexane, and this carbon, carbon number 1, we have a methyl group and a hydrogen, two different groups coming off the ring. If we've satisfied that condition, now we trace the path around the ring in either direction, clockwise and counterclockwise. If those paths are identical, then this carbon is not a stereocenter. If those paths are different, then it is a stereocenter. Is this carbon a stereocenter? No. In this case, we go CH2, CH2, CH2. CH2, CH2, CH2. It's the same path. Okay? So not a stereocenter and achiral. How about this compound? Is this now a stereocenter? Yes, we have different paths, CH, CH, CH2 versus CH2, CH2, CH2. Two different paths. So yes, this carbon here is now a stereocenter. Okay? To save yourself a little bit of time, there are certain types of carbons that will never be stereocenters. Okay? Never stereocenters. The methyl group, never a stereocenter. CH3, we have 3 hydrogens on a methyl group, so cannot be a stereocenter. Okay? In chapter 4, we taught you the word methylene. A methylene is a CH2. That also cannot be a stereocenter because it has 2 hydrogens. Okay? sp2 carbons can never be stereocenters. Why not? How many groups are attached? 3. You can't have 4 groups. So sp2 carbons are not stereocenters. By the same logic, sp carbons are never stereocenters. Question?
Are these rules for in general or only when you're attached to rings?
In general. Thank you for clarifying that. These rules apply to both cyclic and acyclic compounds. These types of carbons will never be stereocenters. Okay? So stereocenters on rings are compounds that contain stereocenters on rings are very important in medicine. This is due to the fact that they are fairly rigid. We know that we have restricted rotation, limited rotation in rings as opposed to chains. And so the substituents coming off of the ring are pointing into very well-defined regions in 3-dimensional space. And so that allows these types of molecules to form very specific interactions, usually via hydrogen bonding, sometimes via van der Waals forces or dipole-dipole forces. But you have very, very specific non-covalent interactions between these chiral molecules with stereocenters on the rings and proteins in our bodies. And another principle related to this is that the 2 different enantiomers of one of these chiral compounds will interact very differently with the proteins inside our body because those proteins inside our body are also chiral. So in the same way that our 2 hands interacted differently, right? We had Tiancum's hand interacted very differently. Was that Tiancum in this class or was that the last class? Yeah, that was Tiancum in this class. Sorry, with 2 different classes, I don't remember the names correctly, but Tiancum's hand interacted very differently with the baseball mitt. His right hand interacted differently than the left hand of our other volunteers. Okay, so in the same way that our 2 hands will interact differently with a single baseball mitt, the 2 enantiomers or mirror image forms of a drug will interact very differently with proteins in the body. And this was most tragically manifested with a compound called thalidomide. Thalidomide has a 6-membered ring here. It has a substituent with a nitrogen coming off of that ring. You see these are mirror images. The R and S prefixes will make sense in about 15 minutes. But this particular enantiomer was excellent at treating morning sickness. It was also used as a sleeping pill. It was found to be a very effective treatment for morning sickness. Any woman that's been pregnant knows that morning sickness is terrible, and it would be fantastic to have a good treatment for it. Unfortunately, in the 1950s, when this molecule was discovered, when you synthesized a chiral molecule, you always got a 1-to-1 mixture of the two enantiomers. It was very, very, very difficult to separate one enantiomer from another. So if you synthesized a compound such as this is a synthetic compound, you would have a 1-to-1 mixture of those enantiomers. So it was given to pregnant women as a 1-to-1 mixture, and it was later discovered, tragically, that this enantiomer caused birth defects in babies. It interacted very differently with the chiral proteins in the body than this enantiomer did. Okay? You can look up on the internet thalidomide babies, and you'll find these terrible pictures of deformed babies where they're missing their arms. They would usually have these little flipper things coming off of their shoulders instead of arms. So very, very bad birth defects. So this drug was stopped very quickly. And fortunately, it was never approved in the US. So the Food and Drug Administration, getting a lot of press these days. There's a lot of heat being put on the FDA to approve a COVID vaccine before a certain date. And the FDA, generally speaking, in its history, has been fairly cautious in approving drugs. Thalidomide was approved for use in certain countries in Europe, but not approved in the US. The FDA was not convinced that it was safe to give to pregnant women. And then after it was given in Europe, these birth defects were discovered, and the FDA's caution was definitely warranted in that case. Okay? Another interesting drug that has rings and stereocenters is paclitaxel or Taxol. Okay? A bigger structure. There's a total of 11 stereocenters in paclitaxel. You could count them and identify them on your own as a homework assignment. This molecule is a natural product. It is isolated from the bark of the Pacific yew tree. It's a very potent anti-cancer agent. It was discovered in the 1960s. The National Cancer Institute initiated a program to try to discover cancer drugs from nature. And they found this in the late 1960s, and about 10 years later, in the late 1970s, they determined its mode of action. They found that it binds to microtubules. It uses hydrogen bonding, a lot of different hydrogen bonding groups there, to hydrogen bond to microtubules, and it stabilizes them and prevents them from proceeding through the cell cycle. It arrests the cell cycle by stabilizing one of the intermediates in the tubulin dimerization and splitting process. Okay? So this was great news. Great anti-cancer drug, but that was a problem in that you can't get very much of it out of the bark of the Pacific yew tree, and if you strip the bark from the tree dies. And the trees are very slow growing, so it's not sustainable to do this, right? You'd have to wait decades to be able to harvest the paclitaxel again from these trees. Another problem is that the Pacific yew tree is habitat for the northwest spotted owl in the Pacific Northwest, and it's against the Endangered Species Act to destroy the habitat of an endangered species, even to benefit cancer patients. Okay? Least you think this is unfair. There was a solution devised to this problem that saved both the owl and the cancer patients. Okay? There were other chemists who discovered that a closely related compound called 10-deacetylbaccatin could be isolated from the needles of another species of yew. And even though this says Himalayan yew, it grows in many different places. It can grow in Europe as well as America. The needles fall off the tree every year, so you can just harvest those and you're not killing the tree. And all you have to do is figure out how to attach the parts of the molecule I've shown in red, and now you have paclitaxel. You bypass the bark of the Pacific yew tree. You save the trees, you save the owls, you save the cancer patients. And indeed, there was a chemist at Florida State who figured out how to do just that. In about 4 steps, 4 simple reactions, he could convert this to that, and he made himself and his university extremely wealthy because paclitaxel became a billion-dollar-a-year drug because it's very effective at treating breast cancer, ovarian cancer, as well as a few types of lung cancers. Okay? So a nice success story in that a solution was found to this supply problem, and it also saved the owl. A plug for preserving biodiversity, right? If we had destroyed the habitat of that owl and destroyed those Pacific yew trees, we never would have found this compound to begin with. And the importance to us now in this class is the fact that this is a cyclic molecule with multiple stereocenters coming off of the rings that gives it a very defined shape in 3 dimensions that allows it to interact with the microtubules. Okay, any questions? All right, so what we need to do now is to learn, to answer your question from before, which is to learn how to name enantiomers. Okay, how can we name enantiomers? Well, we need a nomenclature system. As much as we dislike nomenclature, or at least as much as I dislike nomenclature, we do need a nomenclature system for naming enantiomers, and it's called the Kohn-Ingold Prelog system. These are the 3 organic chemists who came up with this system. And there are 2 prefixes. There's R, which comes, I can't remember if it's probably Latin, rectus. And rectus means right or clockwise. And then S is sinister, which means left or counterclockwise. Okay? Personally, I resent the fact that sinister is associated with left-handedness. That's totally inaccurate in my view. But unfortunately, that's what we're stuck with, is with R meaning rectus or right, S meaning sinister or left, counterclockwise. So how do we apply this? So what we need to do is we need to identify a stereocenter, and we need to assign priority to the groups on that stereocenter in order of 1 to 4, with the highest atomic number getting the highest priority. So let's look at our bromo, chloro, fluoro, methane. Sorry, that's a hydrogen. What is our highest priority group on this carbon? Bromine, what's next? Chlorine, what's next? All right, and then hydrogen is number 4. So pretty soon you figure out that hydrogen is always number 4. Right? That's a hard and fast rule of this. Okay? All right, let's look at our alcohol. Okay. Which group is number 1? OH is number 1. We know that the hydrogen is going to be number 4. But now we have a methyl and an ethyl group. Those are both carbons. So we have to use the first point of difference, something related to the first point of difference rule. We look at this carbon and we ask ourselves, what 3 groups are attached to this carbon that are not the stereocenter? What are they? They're hydrogens in this case. Okay. Then we go to our ethyl group and we ask the same question. What 3 atoms are attached to this that are not the stereocenter? Okay, 2 hydrogens and a carbon. We write them in descending atomic number. Whoops. Okay, and we see our first point of difference. That tells us that the ethyl group is higher priority than the methyl group. Okay. All right. What happens when we have a double bond? Let's make this an OH. 1, 4. A double bond counts as 2 of the group that are doubly bonded to this carbon. Okay? So this carbon is bonded to that carbon twice. So we're going to count it as 2 carbons. And then what's our other group at that carbon? It's just a hydrogen coming off. And then this carbon down here, carbon, hydrogen, hydrogen. Here's our difference. So the methine, or the CH, that's part of the double bond, is higher in priority than the methylene, or the CH2. Okay? So what does this priority mean? So what we need to do now is we need to orient our molecule so that group number 4 is pointing back. And then we need to trace a circle from 1 to 2 to 3. If that circle is clockwise or to the right, the configuration of that stereocenter is R. If that circle is counterclockwise or to the left, then that stereocenter is S. So let's look at the enantiomer of bromochlorofluoromethane that I drew. R or S? S, right? 1 to 2 to 3 goes counterclockwise, so that's going to be S. Okay? What about our alcohol here? Okay, same thing. Okay, what about down here? Okay, 1 to 2 to 3. I didn't mean to draw them all S. Of course, I am left-handed, but I accidentally drew them all to be S. Okay. Yes, but 4 has to be pointing back. And I conveniently drew all 3 of these structures with group number 4 pointing back. What do you do if group 4 is not pointing back? Yeah, that's one way. You don't panic, but one thing you can do is rotate the structure. This shows you ways of rotating structures to put group 4 pointing back. And you have this really nifty graphic of your eye looking down with 4 being in the back and ending up with R in this case or S in this case. But if you're not very good at that, if you're not good at mental rotations, you can do it with your models. Or there's a couple of other things you can do. You can switch any 2 groups on a stereocenter. Okay? And so you would want to switch any 2 groups to put 4 pointing back. Then you would determine R or S. Then you would switch the assignment, because by switching 2 groups, you have now made the enantiomer. Okay, so switch 2 groups to put 4 back, determine R or S, and because you made the enantiomer, then you have to invert the assignment. Okay? There's a third way to do this. If group 4 is pointing out as opposed to pointing back, you do R or S and then you switch it. Okay? So if group 4 is pointing out at you, you don't need to do this rotation. You just switch the R or S assignment. Okay? All right. The best way to learn R and S is to practice. So last thing we'll do today, let's get our eye clickers out. Go ahead and talk to your neighbors. We have a molecule here with 2 stereocenters. We'll talk more about molecules with 2 stereocenters on Wednesday. We've numbered the carbon chain for you. Please assign the stereocenters as R or S, right? Carbon 2 is this one. Carbon 4 is that one. Go ahead and talk to your neighbors and make the assignments. And you can use any of these methods that we've talked about if necessary. Again, we have very quiet conversations going on in here with this group. Okay, let's try to conclude in about 30 seconds, maybe. See if we can get our final answers in. Okay, any more answers? Okay, one more. Good. One more. All right, that's probably it. So we'll go ahead and close it off. Okay. Carbon 2, what's our configuration? R, right? We have OH, that's group 1. The chain to the right is group 2. The methyl group is group 3. The hydrogen's conveniently pointing back. So we go 1, 2, 3, we get R. Okay? Over here, which group 1? Chain to the left, right? We hit the OH as we go left. We don't have that going right, so this is higher priority. So it's 1, 2, 3 is the methyl, and then group 4 is coming out at us this time. So the way I would do it is I would go 1, 2, 3. I would go counterclockwise, but since group 4 is pointing out at us, we reverse the circle and say, okay, that really would have been clockwise, so it's R. Okay, so A was the right answer. All right, go ahead and continue practicing RNS. It's an important skill to have. If you haven't taken the test yet, make sure you go to the testing center soon. And good luck, and we'll see you on Wednesday.